Hi, I'm Junyuan from Michigan State University. I'm very glad to present our paper on differential privacy. Our work shows that dynamic privacy budget allocation can improve data efficiency of differentially private gradient descent. The motivation for our study is from the increasing concern in reality. For example, the general data protection regulation limits the data sharing or usage in any machine learning algorithms. So it's very important to study how can we effectively train a model by using very limited data and preserving privacy. Otherwise, the privacy may encounter a lot of risks in reality. For example, data leakage may happen from the trained models. The most common practice is to adopt a differentially private stochastic gradient descent, where the gradient will be privatized by noisy mechanism. First, we will clip the gradient to a specific sensitivity. That means any missing one gradient will not make great difference, a bounded difference in the update. And we will calculate the privacy cost by the noise scale that will be used later. If the privacy cost is not over the budget RT, then we would analyze the gradient by a Gaussian mechanism. Then we release the gradient and the current privacy cost. Recently, studies have shown that differential private gradient descent will require more data. In this table, we also demonstrate that compared to non-private gradient descent, the privacy cost significantly increased by state-of-the-art differential private gradient descent. For example, using the advanced privacy content in the first line shows that an additional logarithm term of the data will be included in the utility upper bound. Another problem in the private learning is that the convergence is very difficult. The main reason is that because of the constraint in the privacy budget, the learning can only be executed for a few iterations with some very large noise. So the utility will be very poor. So our goal is that how can we improve the final iterate loss given a privacy budget? That means we want to minimize the gap between the private model performance to the optimal model performance. We call this term as the upper bound of the expected risk. Why do we have to study such a convergence upper bound? It at least bound the worst case that we'll encounter by using the differentially private gradient descent. Also, it can help us to find a way to speed up the optimization algorithm. To study the impact of privacy operations like noise mechanisms, clipping norms, and so on. And finally, we will be able to compare different algorithms without any assumption on the hardwares. In this paper, we made the following assumptions of the algorithm. Let it include the G-Libshez continuous loss, which will not be quite different given the similar input. Secondly, we assume the gradient are M-Libshez continuous, which is also called M-smoothness. Last, we assume this loss function is actually some polyarc Zhou condition, which is a weaker assumption compared to some prior work using mu strongly convex. With these assumptions and our algorithm, we show that the we show the upper bound on the expected error by using a dynamic noising magnitudes in terms of the sigma t. We also show that the sigma t has a exponential influence on the final on the convergence upper bound. To be more specific, we see that the first term in the upper bound include the convergence of using finite iterations t. Then the second term shows how this noise will impact the final convergence. Because the qt is an exponentially decreasing term, so the influence of the noise will be decreasing by increasing by iterations. So later inspires us to design such a noise schedule such that we can extend the effective iteration number, and we can reduce the effect of noise by put the weight on smaller noise. We propose such a dynamic schedule in terms of the derived influence on the final iteration. We show that this because of the qt should be exponential term, so similarly the noise schedule should be also exponential. We clearly show that the advantage of our method is can extend the number of iterations to be allowed within finite budget compared to some uniform schedule. That means the noise magnitude will be constant during training. In the left figure, we show how can our method extend the number of iterations in the y-axis, and on the right figure we show that the error upper bound will be reduced by using our method compared to the uniform, and the approach is the non-priority algorithm. We also accurately check how can we estimate the influence, and we show that such an estimated influence by retraining the models for multiple times will be exponentially increasing. And by adopting this exponential dynamic schedule estimated by the qt, we find that the final loss can be improved effectively. We also study other variants of the stochastic gradient descent. We show that by using momentum can further improve this method. By momentum, we mean that the gradient term Vt will memorize the previous gradients and to smooth the updates, which may somehow reduce the variance of the gradients. And finally, we show that the upper bound will be improved by introducing a negative term if the learning rate is small, and which is because of using the momentum. And still, the noise term will be exponentially, but the influence will be more complicated. It will first increase quickly, and later will be steeply dropped into a very small value. We show that our method by using the exponential dynamic schedule will reduce the privacy cost by which sample efficiency will be very close to the non-private term, actually less in the same order. Similar conclusions are for the momentum variant. Thank you for watching our video.